So today the schedule is like this one. Okay, so we had a nice lecture from Professor Na about worship design last time. And today, probably I will start with the second part of ship dynamics, ship motion. And then we may go on to discussion led by Barakat, and then lecture by Adiba. That probably be the schedule for today. All right? Any question? No? Then I can continue or start my second part of ship motion. And so this is the book we are covering. And chapter is dynamic stability or ship motion. And the previous part is covered by Ki-Han Kim last time. So I will cover later part, second part of rollers, pitch, and yaw. There is a three motions, angular motions, and feedback control to reduce side effect of the motions. So 6 degrees of motion of ship already shown. 3 translational and 3 rotational. So you see that the terminology are very special, especially the surge and sway and heave and yaw. But if you learn this kind of new terminology or strange terminology, you can use it for another situation, like airplane they use, or space shuttle, or sometimes the car also use that kind of terminology for the motions. So it will be help. And because of this traditional historical reasons, they have been used for several hundred years. Roll motions is coming from wave forces, especially the beam C means wave is coming from sides rather than wave coming from the front. The crest line is parallel to the ship length, so wave is coming from the side. We call this as a beam C, and it can cause roll motions. And wind forces and cargo shifting. Cargo is moving. We heard that for Korean students, one of the reasons for capsizing of Sewol is cargo shifting, containers and cars inside the Sewol. And rather hard over. So it is also, some people are saying this is the one of the reasons to capsizing of Sewol ship. Hard turn that can create a small healing moment. And disagreeable aspect of rolling motion is possibility of capsize the Sewol, and motion induced inertia forces. There is an acceleration inside the ship. If you take a car, car is turning around very fast, then you can feel that your body is shifting to another side, right? Or bumping in a rough road, that you can feel some uncomfortable motion-induced inertia forces, accelerations, and that can hurt your body, your feeling, or you can have a sickness. Right? So that is all related with motions and acceleration and speed. And how to prevent cures? We can use meta-center height again. GM is used, we learned for stability, that is for static stability. But we are now talking about dynamic stability. And GM is also has a effect on roll motions. And here it is saying modest value rather than high value or low value. In static stability, higher GM is preferred, but now it is saying modest. It is saying, you can say there is an optimal value rather than bigger is better or smaller is better. Because you can think about the spring constant of a car, or you know what is shock absorber of the car. Shock absorber means when the car is riding on a bump area, the shock absorber observes the shock coming from the road. But if the spring constant of shock absorber is small or big, then your comfortability level is different. Right? If K is small, the feeling of passenger comfortability usually high. But it is too small, then it can, how can I say, observe all the bump coming from the road. It cannot observe all of them. If K is too small, it is very similar to spring constant of F equal Kx. And if K is too high, then it is inside the car seat. It is very similar to riding on a bump. It is very bumpy inside also. So it is not comfortable. So that's why we need to have a modest value of spring constant or something like a meta-center height. And another way is putting a special device called roll stabilization. And there is we already see this one coming from Hyun's lecture: Bilge-Keel, stabilizer fin, anti-rolling tanks, and rudder roll stabilization. So roll stabilization, wave create rolling motion. Right? Wave is bumpy, and then the stabilizer, what device it is anyway, the tipping force and compromised by stabilizer force. So balancing of forces, that is the key point. How to balancing these forces. So how to manage this by using special kind of devices. And Bilge-Keel, usually it is a static and protrude as a plate, steel plate, approximately perpendicular to the hull, the skin of the ship. Near the turn of the bilge, there is a corner of a side corner, but side bottom corner. We call this a bilge, turn of the bilge. And typically length is not 100%, it is less than 50% of the length. And if we put Bilge-Keel, that helps to increase added mass or damping of the ship, so that you can think about also again the spring mass vibration equation, and there is a damping coefficient of C, and there is a mass and K, the spring constant, and C is the damping coefficient that is dependent on velocity of the motion, right? And fin stabilizer is a special device with the engine or power, and the fin angle can be controlled by the captain or person. And retractable, so left hand side bottom, the angle of attack is controlled by some device. Right hand side bottom, the fin itself can be retractable into the ship body. So when there is no need, it is folded inside the ship. And only when the fin is necessary, then it is protrude by control. Because of when the ship is passing through the shallow water and also near the keel or port side, then the fin can be damaged by the structure of the port. That's why we sometimes need a retractable ones. And there is a mechanism of anti-leveling tank. You see the video. There's no sound. Anyway, so this is using effect of free surface effect can be used to stopping. If we not using the girders between or structures between walls, then it is less moving, right? Less moving, right? With the same platform motions, because of the side effect or surface effect. But that is not active motion, right? Active motion. But there is another one called the real device can use is sound, yeah, sound is on. So the active stabilization is working, then the water level of side tanks are controlled by pump to compensate the roll or heeling moment. So they are saying roll compensation. So there are two side tanks, and the water level can be controlled by pump and by captain, human. But the problem is the speed of pumping, right? So that is should be the pump size and piping diameter should be decided based on ship size and ship motion estimation. And pitching is another way. So that's it. Okay. Any questions? No, then we can continue. That anti-rolling tanks, there is two types of U-tube tanks. U-tube means the shape looks like a U, shape of U, right? And there is sometimes a pump, and there should be a valve. So this is active control or passive control. And by using only valve opening or active one can push water flows. But anyway, the shape is U-shaped tube. And rudder roll stabilization, the rudder can make a force based on lifting forces of the flow, very similar to airplane wings. And based on rudder force, there is a roll moment from the rudder is coming. So hard turn, very speedy and big angle that can create a small roll moment. But depending on the ship, then it is the several case can maybe the small reason. Okay, and so that there is a Bilge-Keel stabilizer fin, anti-rolling tank, and rudder roll stabilization. There's a comparison with the advantage and disadvantage. Bilge-Keel is very simple and inexpensive. The resistance of the ship is increased because of the wet surface is increased. Stabilizer fin effective, but it is it is not effective at low speed because of the VR. You should use lifting forces of the fin, and also it is expensive because of the mechanism. Anti-rolling tank it is effective in all speed range. Ship speed means ship speed. Stabilizer fin is not active at low speed of ship, but it requires a large space for tank, water tank, the U-shaped tank. And rudder roll stabilization, small space, but it is not effective, same as lifting force is used. And also steering system should be bigger. There are other ideas like spinning gyroscope or Bessemer's saloon, very similar ideas. So, or using inertia forces. I will not show you the YouTube this time. You can have your own time. And so dynamic stability, not static stability in roll. So equation of roll motion is like this one. It is angular motion, so that there is a second derivative of angle phi, and first derivative, the velocity, angular velocity, angular acceleration, and angular position, angle itself. So it is very similar to spring mass vibration or motion equation. So inertia term and momentum term and then spring term. So this is spring constant, you can say. But each parameter here is very complex equation itself. Ix and K and Kp dot and Kp, and also mass and G and GM. GM is here because you know that how to calculate GM over ship is not simple. Okay. So pitch motion, that is another motion rather than roll. So up and down in front and back. So it is coming from wave forces, but wave is coming from front rather than side. That causes pitch. And ice breaking motion for icebreakers, because icebreakers breaking ice is by using ride on top of the ice and then press down to break the ice by using ship's weight. And once the ice is break, then ship is plummeting down into the water because there is no ice resistance. That's why the pitch is coming. The bad aspect is sea water on the deck. If the pitching motion is big, then water is coming above the ship on the deck. And then also the slamming. Slamming is the wave is hitting the bottom of the ship at the front. and it is big, then sometimes the skin of the ship, the steel plate, can be damaged. And if the propeller is above the water surface because of pitching, then propeller is running very high speed because water is not there. And then also inertial force is the same as the roll. Cures, you can change the course direction of the ship, and also speed can be changed to reduce the pitching motion. And also load distribution means the cargo weight can be distributed properly to reduce the pitching motion. Also stabilization fin can be used for the pitching motion in different direction. So let me show you what is the slamming of the sea. This is container ship. Okay, so you see that water is coming over the ship up to the containers. Right? So you only see that video, but if you are staying inside the ship, then it looks like a roller coaster. Right? So it can be very rough sea. And pitch motion, the equation of pitch motion is very similar to roll motion equation, but different angle, theta. And this is a acceleration term, inertia term, and moment term, and spring constant. It looks similar, but each parameter term is very complicated and different. And you can remind that the mass spring damper equation, here is something like this one. X inertia term, second derivative, and damping coefficient of moment term, and then spring constant. K, right? K. C is the damping coefficient, and M is a mass. So this is inertia and external forces. So you can remember that F equal M A is acceleration, and CV, V is speed, and then K is spring constant. All this we learn from mechanism or vibration or dynamics or mass and spring constant and damping coefficient. And so that is very similar to this equation, right? The format is same because it is also motion, but the parameters at front is very different and also very complicated because ship is big and complex. Yaw motion is rotating around the vertical axis, so it is swinging. Causes it is also wave forces, oblique wave we say. And vessel towing means sometimes the ship is towed, pulled by another ship, tugboat we say, tugboat. Then in that case, it is yawing going right hand side and back hand side, swinging in these days. And bad condition is coming from course deviation because of the yaw motion is angle, directional angle is changing, so that we want to go to that direction, but ship is going the other direction. And broaching can be another problem there. You see that what is broaching, and how to remove that is trim by stern, so that ship is more submerged by the stern, or using rudder steering to correct the direction of the course. And there is also NTO scale. And at the right hand side, you see the small boat photo image that shows looks like a double catamaran, double hull. But also you see that vertical scale, we call this is plate at two sides, both sides of the ship. We call this is the anti-yaw scale. And broaching is something like this one in sailing yacht. Because of the yawing motion, it can create the sail is collapse because of the angle of attack is not correct position. So the sail failed to make lifting forces. And yaw stability, we call this is a directional stability. One is a state line instability, means if once there is a disturbance, it is going that direction as it is. So you can remember that the previous case of flat surface. What is the name for stable, unstable, and what is it in the middle? Hyun, can you remember the name? Stable, unstable is a concave and convex, and then flat surface, there's a roll, circle, semi? No. Anyway, the directional stability, it is good for the ship captain so that you can return back to the original straight line course. Right? So it's called as stable. And unstable means, it is positional stability, means you return back to the original position and also direction. So the third one is more possibly better. Right? Here is stability and maneuverability is related with stability, the returning to equilibrium state after the external disturbance. This already shown, but maneuverability means reverse way, the capability of moving a vehicle out of its equilibrium state to a desired state. So something like a good turning capability we call the maneuverability. So stability, course keeping, and turnability can be some competing capability. So we need to have a trade-off as a designer: course keeping stability or maneuverability. So course stable vehicle tends to stay in its course equilibrium, so it is not easy to maneuver. Right. So you may think about the turtle ship of Lee dynasty. That turtle ship is good for maneuverability. So turning is very good, but at the other side is course stability was not good. So there is an autopilot system that helps you to course keeping without help of the human body. Nowadays, the cars, automobiles also trying to adapt to this kind of autopilot. It was very popular in airplane. autopilot is very popular. Now also ship is using autopilot, and it is coming into the automobiles nowadays. And there is an equation for this autopilot, motion equation, and also feedback control. Nomoto is a person from Japan. He developed this equation, so it is following his name. And dynamic positioning is something like you need to have several propellers. You cannot see here, right? There is some small propeller you see here. So you can keep the position keeping because of the several reasons. One is you need to have a pipeline coming from the sea bottom so that the ship should be stay there. Otherwise, the pipe can be disconnected or break. Or another case is there another ship is coming to deliver oil or gas to transfer between ships. Then you also need to have a position keeping. That kind of things are used. Okay, that's it for today. Questions? No. We have one person missing today. Anyway, then we can go on to discussion led by Brackett, please. Audio on, please.
Oh, okay. I'll share my screen. Can you make me a host here?
I did.
Yeah, actually, put in looked plugins.
Let me try again. All right. Brackett, yes. Try again. Brackett, I cannot hear your sound. Can you turn on your video, audio? Oh, he has a problem with connection.
Having a problem with his Zoom.
Then in that case, we can start Adib's lecture first. Adib, can you do it?
Sure, Professor.
Brackett, your discussion will be after the Adib's lecture, please.
Oh, okay. I had problem with Zoom, so I
Right. Yeah.
looked back.
Can you see my screen? Okay, alright, so today's select lecture will be about the resistance and powering of ships. So at first we're going to talk about ship resistance.